Hello everyone, this is Bradley. Today this is a quick tutorial to make the procedural circuitry in Blender using geometry nodes. I'm using the version of 4.0, but it's just for convenience to make the tutorial. You can do similar kind of thing in 3.6 as well using simulation nodes. So let's start. So here we're in Blender. Let's go to noding. Unfortunately, screencast key is not available in 4.0. I think they've changed some Python API, so the old plugin no longer works. But I think it's worth to make the tutorial now in case I don't have time in the future. Okay, so let's create a quadrilateral. As always, I'm going to use the preset which you can download for free from the link in description. But essentially, there are many more presets I'm going to use. Firstly, it's just curve points preview is just to visualize the points, because I want to show that there are only 4 points now, but I'm going to resample the curve so that I increase the amount of points, so maybe increase to 20. You want to always start with some simple setup and then make it complex in the future. Okay, so we have a resampled curve, we have all these kind of points, and I'm going to instance curve on these points. Basic idea is that, for example, I have a curve line, for example. Okay, I have a curved line and I want to append a point at the end of this curve. So there's a preset called append points to curve. Currently there is nothing happening, but if I combine X, Y, Z, and if I goes to X, then you can see there's an offset of the last point to this direction. Okay, the principle of this append points to curve can be pretty simple. For example, I have a curved mesh, and then I extrude the mesh. By default, it's going to the face, but we can extrude the vertices, and basically we can just combine X, Y, Z. We get a similar kind of result. Of course, you have to tweak a little bit more settings like the selection and the point selection, for example. But it's a lot more setup, which I'm not going to take care of for now. Okay, the actual implementation of this preset, however, is a little bit different. I use a different method, but you can do the same with extrusion. Okay, so now which means I need the curve points. So I have a preset which is 2 curve points, which is essentially just the point instancing the curve onto the points you see. Okay, so I take up 2 curve points. If you disable the preview, you do not see anything because it's just a single curve points. So yeah, and we take a repeat zone. I'm going to take these repeats and I'm going to append points. Right now, you do not see anything happening, but I'm going to add an offset. So we capture the normal. I take a normal and I can feed this normal into the repeat inputs, and we feed that into the repeat output. Because this is a constant, we take this into the offset. So you can see now we have a curved line being generated. And by increasing the amount of iteration, you have more points extending more and more onto all these kind of curves. So we have the basic circuitry being done. However, these are just straight lines right now. These are very boring. So we are going to add some noise. Here I'm going to use the vector rotate, which basically determines if it rotates 45, negative 45, or something like that. Okay, so I'm going to add a noise texture to change the direction. I can use the 2D noise since this is a 2D setup. And within factor, I'm going to use a map range. Here I'm going to use the stepped linear because I want to have a more static, how should I say, more constant changes. So I do not know the radians of many angles, so I'm just going to use the 2 radians so that I can type in degree into this minimum and maximum. Here I'm going to type the negative 45 and 45 and the step size into 2. This actually means that I start with negative 45 and I reach 0. So this is 1 step, and reach 45. So this is the 2nd step. Okay. And this noise texture, if you visualize it, you will find this noise texture is not actually starting from 0 to 1. It should, but it's not. The reason is actually due to this roughness. So we decrease this roughness, we have a more variations compared to before. Okay. Also, you can clamp it. So 0.25, 0.75. So you have more variations. These are all ways that you can potentially do. Okay. Despite the intersection, this is working well. You can decrease the scale so you can make them more organized. Here I'm just going to use a value precision, which is essentially a value divided by 10 in this case. So that we can have a more fine tweaking of all these kind of values to pick up something that you potentially wish. And you can see the relationship between all this kind of noise texture and its angles. By increasing the count, you can see how they are organized and so on. Something like that. Okay. So these are currently just the examples. But we're going back to the resample 25 for now. Right now, we have lots of intersections. And it's very annoying if you think about that. So we are going to remove the intersection. And how can we detect curve intersection? If you use search, you will realize there's a preset called curve intersection detection. It's basically the byproduct of this setup, but I'm not going to use it because I don't like it. Maybe someday I will delete this node completely. It's working great though. But I'm going to teach you how to break it down. The entire setup, the entire concept is very simple. You just use recast. Okay. But the recast does not work for curve. So we need to curve to mesh. So we curve to mesh. Once we made a curve to mesh, we need to extrude that to create a face. So we extrude edges. If we directly visualize the setup, you can actually see this extrude mesh is based on normal. And the normal of this curve are crazy. So we, instead of using normal, we just use an offset. And we need to transform that to offset a little bit. Maybe negative 0.5, so that this point can actually hit the face. Okay. And we're recasting with points. I'm going to use the endpoints. So let's separate geometry to take a endpoint selection. And I'm going to sample index. Here I'm going to sample the vector, which you use to offset all these kind of curve points. I'm using the endpoint selection so that I can get an endpoint of every curve. And basically, I'm doing a forward intersection detection to see if when I'm moving forward, for example, this particular point, when I'm moving forward, does it hit this straight line or this straight line or something like that? Okay. So we have the vector. We have this vector rotate, but I'm going to scale that if it hits. So we recast it. If it hit, then we take a switch. We switch with a float. If it hits, we then do not move. If it doesn't hit, then we move. And I'm going to sample this result to our append point to curve. And I'm going to use the index. And I can apply this value to the offset instead. Okay. But you see it does not really work, or maybe it's working. But there are many issues with it. So here, if you think about it, we are essentially recasting to itself. So we start from an endpoint. But this endpoint is also a part of the mesh we created. So this is how recast can cause problem because everything will actually show kind of positive at some moment. So here, actually, there are several things that I need to deal with. One is the redirection. Yes, if we use the redirection, you can see there are lots of points being deleted because they are all showing positive due to the overlapping issue I've discussed earlier. So I'm going to use the position to add a little bit offset. So scale offset. And we add these two vectors together. I do not want to add too much, maybe 0.0001. Just a little bit is enough. And we take the source position. So now we recover it, but you can see it's not working too well as expected. The reason is very simple. If you try to, let's go to the iteration, let's use the group input so that I can control this value in the panel. Let's go to iteration. So we start, you can see the first intersection is because that I'm doing a forward iteration. So if I already have a curve here, then this curve will know that I'm going to hit this wall, so it will stop. But in this case, we start from nothing. And then we all add points to make the intersection. So it's unavoidable. So this is a bug or an fundamental limitation with this current method. Okay, can we solve that? Probably yes, but it will be too complicated, so I'm not going to solve that. The second way to solve this, in this case, is just to decrease the amount of scale of your normal. So we take a scale. I'm going to take maybe 0.1. So let's take a value precision. So again, this is just the value divided by 10. So by 0.1, you can see they do not overlap each other, and you play the iterations. It's not perfect yet, but you get some idea. You can see there are some part which is working, and this is how it works. Okay, so we take another count into the group input. We can take a stress test to increase the count. You can see it's not working perfectly fine due to many other reasons. For example, you can see that these 2 points are intersecting due to the reason we mentioned earlier. Like initially they do not really intersect, but they intersect because both of them they pass at the same time. So this method is not perfect, but it's working. If you zoom out, you may not realize there's tiny problem with it. And we can increase the noise to make the setup more interesting. And if you want, you can change the seed. Do I have a preset called vector seed? Yes. Essentially, it's just a vector adding vector. So we can change the seed. It's completely procedural. Change the values. 10. Okay. So this is kind of our idea. Okay. For now, this is the simplest setup for this thing. But in reality, it would be better if you add branches. But adding branches will make your life miserable. Therefore, here I recommend you to duplicate your node tree in case you've done something wrong later, that you have a milestone to go back. Or maybe you are just satisfied with the result now, you don't want to go further, because it's really miserable. So let's start with a join geometry. And the basic principle of branching is pretty simple, however. It's basically just duplicating yourself. But here I'm going to use a curve 2 points. Two curve points. We are going to separate the geometry actually. Separate the geometry. And I'm only going to take an endpoint. So that I'm only adding a branch, a new branch at the endpoint of every iteration. So that every point can potentially be a point of branching once you are increasing this iteration. Okay. The reason I'm doing this is because I don't want to increase in iteration. There are new points coming from everywhere. It will be an exponential growth and a crash of Blender. Okay. And I'm going to add a second condition. The second condition is I'm only going to add branches after maybe 5 iterations. Okay, so here I need to know which iteration I'm in during this loop. So here I'm going to take an loop index. The principle of this loop index is very simple. It's basically just adding one number every time for the loop. And here we need to go back to the end of this loop so that we can feed in this loop index into it. So if you add 1 every time, so it starts from 0 and it becomes 1 after this loop, and this 1 will go back, and you start from 1 and you add 2, you get know which iteration you are on in this case. So maybe we'll take the first loop index. If it's greater than 4, then we start to do this branching system. And I'm going to add one more condition, probably 2 more. The second condition is that I'm going to add a probability. So take a random value. So only 10% of all these kind of endpoints will generate a branch. Okay. So this is the current idea. So now if I add this separate geometry back to join geometry, you may not really see any changes. Okay, it becomes very crazy. This is why I say this is miserable, because you want to do the changes after. The order is very important because you want to have enough index being generated during this process. Okay, but we do not see branches. The reason is that the noise texture is based on the position. There's a position inside, but the position of all these kind of endpoints are the same because they are coming from the same geometry. So we're going to add a seed when new branch is being created. So the way I'm going to do that is to store named attribute. We store a point, an integer, and then maybe I store whichever loop index, maybe front, back, does not really matter. Let's add a G generation. So we take a named attribute, and I take a G, and I add them together. Actually, this integer and the vector mass is the principle of the vector seed I have previously. They're basically the same. Okay, so now we see the branches. And you can see, because we are branching, it creates more bugs, but this is it. Here, I'm going to do some changes to improve this setup. So one thing I want to do is I want this branch to move in a lesser scale compared to the main branch. So I need to deal with something with generation. Our generation starts from first, and we have second, third, fourth generation of all these kind of branches. And by increasing amount of this G, I want this vector scale becomes less. The way I'm going to do is to use a formula. The simplest formula is 1 divided by x. So the first generation will be full scale, second generation will be half scale, third generation will be 1/3 scale. Okay, so this is the idea. So we run a division, and I'm going to duplicate that. So 1 divided by this G, and plug that into this result. So immediately you can see they are shrunk too much because it's half, third, 25% of the original scale. That's why I have this first division so that I can divide it by 10 to recover some of the length. I'm also going to make the decrease or decrement, whatever you call, in a lesser degree. So I'm just adding 0.5. You can see this graph on the graph calculator, or you can just tweak the value. Even if you do not know the math or how the graph actually looks, you can just try and you get this kind of result. Okay. And one more thing I realized is that at this kind of corner, these normal are not really parallel to each other because they are influenced by this corner normal. So the way I'm going to fix that is I'm going to capture this normal before. I'm going to capture this normal before my resample. And you see it's not really recovering. It actually becomes worse because initially I only have 4 points. So the influence becomes larger when they are interpolating. But I can add a new resample in a high resolution so that the normal I'm getting is very accurate, and then I'm reducing the size of my curve to solve this problem. Okay. There's one thing that you can do as well. Is currently this is a rectangle by using this quadrilateral. What if I want to add some bevel to that? So when we're working with curve, it's not called a bevel curve. It's called a fillet curve. So that we are adding a kind of corner to that. And now if we disable that, you can see there are more corner being generated. You can even change the shape of our chips in this case. Okay. So eventually it's completely up to you. Everything is procedural. Okay. I think this graph looks nice. And the bug is less noticeable as well. Yes. And you can increase the count to make it look better, and so on and so forth. You can change, everything is procedural, you can change that. And the third thing I want to do is, right now everything looks fine. You can see the real changes in the viewport, but by increasing the iteration, you're increasing more points. Then until a moment it actually frees your computer, it becomes 5 seconds. So it becomes very dangerous. One reason is that I'm always appending a point to the curve. So even if this curve is no longer extending itself due to the collision detection we made, but I still add a new points every iteration. So there are probably billions of points being generated. So I'm going to do a selection to only append the point to the curve which needs to extend itself. So the simplest way I think is just to add a length. And the length will be 0 or above 0. So I can directly plug this into selection. So you can see that originally it's 124. And by putting into the selection, it's reduced by half, and graph is changed a little bit as well. But anyway, this is kind of idea. Okay, the graph is changed because the internal concept is using the separated geometry. If you do not want the graph to be changed, you can capture the attributes. And it should be a spline domain. These are just something that you can do. It does not mean you have to do this, because whether you do that or not, sometimes it does not really matter in my opinion. Okay. Next, let's add a material to that. So in order to render this kind of curve, you need to give some thickness. So let's take a bevel curve and 0.01, something like that. Maybe 0.02. And take a resolution to 32. And I'm going to store eevee map, which is really just a store named attribute. And I set material to give it a emission shader. So within shader, I can put that into an emission shader, and add a wave texture. Starting from 3.6, all this kind of UV, if you stored at the face corner domain, it will be read by this texture coordinate. So if we go to material preview, you can see everything is following UV and you can animate it. Okay. But in actual rendering, I noticed a problem that the actual amount of branches are less than what we see in the viewport. The reason is that even if we're using a different seed for the noise texture to make branches, it does not mean that these branches were not following the same direction as the main curve. So for example, I have a main curve here. It's very possible that I created a branch, but it follows the same direction, so that I do not actually see it. To solve this problem, we're again going to add a new vector rotate. A second vector rotates based on the original result. And here I'm going to add a switch of vector. So if I'm generating a new curve, then I'm rotate the second time, otherwise I only rotate it one time. And I plug that to replace. Okay. So how do I know I'm generating a new curve? I'm going to use this generation. So if it equals to the current loop index, which means this is a branch newly generated now, then I'm going to switch this vector. Okay. But how do I determine the angle? The angle will be basically the same as the noise texture, but I'm going to use step 1 so that I goes directly from -45 to +45 without a 0. So now if I plug that in, oh, actually, I do really have new points here in the same direction. That's why I do not see it earlier, but once I add that, it becomes visible. Oh, it's a coincidence because I don't know. So you can see the graph changes a little bit because the evaluation and noise being different, but you can actually see more branches are actually created during this process due to these changes. Okay, so this is it. The last thing I'm going to do is to trim this curve. Here you may wonder that this entire setup is built based on the iteration. So why don't I just run the iteration to build this setup instead of trim this curve? The reason is pretty simple. As you realized earlier, that if the iteration goes too high, then it will freeze your computer until it crashes it. And you don't want to do that. But if you're running an actual animation, maybe I have maybe 200, 300, 5 billion frames, you do not want to use the iteration in this case, because it will cost 5 billion iteration, whatever. It's not possible. Of course, you can use the simulation node, and to replace this repeat zone as using simulation node, it's basically the same. You basically do everything the same. The only difference in this case will be, instead of using the loop index, I'm just going to use the same time to replace everything. And you do not even need to pass the same time. You can just use the frame number into the result. Okay. So this is basically the difference between simulation node and the repeat inputs. So you have the simulation node. Okay. And the reason I'm using repeat inputs is mostly because I do not want to change the parameter and keep playing this animation. It will be so crazy. And the second reason is I think in real life, it's more possible that you build an actual circuitry using repeat zone instead of running the simulation every time. Okay. So how can we actually trim this curve? Right now, if I trim this curve, then you will realize it's based on the parameter. So that's the new branches will be trimmed as well. And they're not at the same time, so you have this weird graph. Very often, this is not what you're looking for. So you need a gradation. And to add this gradation, we need to store a new named attribute, basically the length. This time is a float. And this attribute, I think it's before this separate geometry. So I add spline length to named attribute to the length, so that I'm building values for every branches. So once this is done, once this is done, we can use a length. So I have a subtraction. Let's name the attribute. I subtract this length. And use this value to do that. So now you can see, as I'm passing these points, branches and the main branches are moving together. Okay. So this is it. One kind of thing you may also realize, because I created these kind of points during this loop without them extending themselves, it's maybe ugly in the viewport, but since it's not rendered, you may not care. But if you really do not want to see them, you can delete geometry. And if the spline length is equal to 0, actually we can directly plug this length into the selection. So now I delete geometry, delete the spline into the selection, and I take a knot. So I do not see this. So now by playing this subtraction, you can deal with it. And if you want to add some variances, I may not talk about how to add variances of this trim, because it will make this tutorial too long. But should I? If you want to add variances, you want to synchronize the variances. So the short answer is I'm going to capture an attribute. So here, because they're spanning too long within the node tree, I'm going to capture the index. And I'm going to use this index at the end. So store name that we'll use the named attributes, and this is the index. I'm going to take the motion variances, plug that into the custom ID, and so now you can actually see there's a kind of randomness in the speed instead of being a circle. Okay. So this is basically it. There are potentially more things to do. For example, you can try to solve these intersection problems, but I'm not going to go further. So I hope you enjoyed this tutorial. I'll probably see you next time. Bye bye.